All right. So record player 33 1/3 revolutions per minute. And so what I'm asking you to sort out there real quick with your friend is what is the period of that record player in seconds? Did you sort them out?
Yeah, they didn't know how to say my middle name.
So we're talking about the record player. We know it's listed as having a rate of rotation of 33 1/3 revolutions per minute. So we're trying to figure out how many seconds per revolution then. Ballpark 2, right? This is if it did 60 revolutions per minute, it'd do 1 revolution every second. It's only doing 33 1/3 revolutions per minute. So it's got to be taken somewhere in the ballpark of 2 seconds per revolution, yeah?
Yeah.
1.8. 1.8? Yeah? I'll buy it. Eddie looked me in the eye when he told me, so I trust him. All right. So the period for the record player, 1.8 seconds. What's going to be the relevant info for the spring mass oscillator? Ooh, I should give you some relevant info there. So I collected some data earlier, okay? And I got for the spring that we're using here, let's see, the forces and the delta x's. So 0.9 newtons went with a stretch of 0.1 meters. 1.6 newtons went with a stretch of 0.2 meters. And 2.3 newtons went with a stretch of 0.3 meters. So hop on over to Desmos and see what kind of a best fit line you get there. See if we can't get a value for K for this. I can't wait till this ends up being like one of the AP questions this year. It's like a record player, a spring mass oscillator, and a pendulum. It's gonna happen. Some year in my career, we're gonna win the lottery. This isn't Desmos. I'm just drawing it. But if you actually Desmos it, see what kind of a value you get for K. And then once you got that K, check it with your buddy. If I do it the quick and dirty way, I kind of get somewhere in the ballpark of 9. Where are you guys landing with Desmos? 8? Did you do Desmos or did you do it the quick and dirty way? Quick and dirty. Anybody Desmos me? Humor me? Not assume this thing goes through 0, 0? Because it doesn't. You did it backwards. Don't do it backwards. So a more considered graphical approach leads to a slope value of,
6.6,
I got a 6.6.
8.1.
I got an 8.1. Six point six, 8.1. Clock is just going to go ahead and calculate the regression. Mr. Witt happy. 6.6, 8.1. Anybody else for slopes? You got 7.8, 6.6, 8.1, 7.8. Granderson, I've been staring at your computer there. You got anything for us?
Right around 8.
Right around 8. We're circling the drain of somewhere in the location of 8. Just go with 8. All right, so then if we've got a period of 1.8 seconds, if we divide that by 2 pi, that gets squared, multiplied by that k, that should give us the mass. K is 8, so therefore, how much mass do we need to oscillate? So get a number, double check it with your neighbor. Hopefully it's something that's doable here in terms of classroom mass sizes.
Kilograms.
0.666.
I guess so, yeah.
6.
Spawn Satan over here has got 0.666 kilograms. Carwell agrees. All right. All right. And then the other one, this is in the mastering / in the readings / the equation sheet. The period for a pendulum, 2 pi root L over G. L's the length. So how long does that need to be? Well, again, we want a period of 1.8 seconds, 2 pi. But here we're going to multiply by G by 9.81 newtons per kilogram. And that'll give us L. That should be in the ballpark of, oops, Mr. Harding. I forgot to square that there. So T over 2 pi equals root L over G. So then we square both sides. And then we multiply by 9.81 newtons per kilogram. That'll give us the length. Ballpark 0.81 meters. Okay. So we've got a length of a pendulum. We've got a mass of an oscillator. We've got a record player. So let's go give this a sniff, see how it shakes out. Oh, good.
One's for a pendulum and one's for the bottom one's for a pendulum and the other one's for
All right, so that's the ballpark. And then this part itself is 0.513, and we need 0.66. Let's see. 513, 0.613, 0.668. All right, so that's the ballpark. So let's check it all out. How do we do? Pretty good. Pretty good if our goal is pretty bad. Okay. How about the pendulum? Is the pendulum at least okay? The clock running fast or slow? Fast. Like the pendulum makes it back across the goals. You need to make the pendulum shorter or longer? What are these questions? All right. How much? Yes, and check. Yes, and check. Through there. That's close. Do you see how the shadow of that pendulum is being cast on the record player? How that mass is going through that shadow. Ready? Everybody. Move, 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 move. Okay. So let's check it out. How long is this? Actually, a little bit longer. This is about 0.91. 0.91 meters. So perhaps, and I kind of already knew this because I don't use square root anymore. It's slow. Perhaps the record player is not actually rotating 30 degrees. If the pendulum period is if the pendulum length is 0.91 meters, what does that mean for the pendulum period? Okay, let's scurry back over here real quick. Turns out the record player is a little slow. So what is the period of the pendulum if the actual length is 0.91 meters? It sounded painful. So we're just changing the length. What does that change the period to? Changing a lot or a little? Okay, what'd you get?
It was 1.91.
1.91 seconds. Right, because we changed something and then we square rooted. We changed something a little. We changed the length a little bit and then we took the square root of that. So that's not going to result in a big change in the period. 1.91 seconds. Okay. Ooh, but if I throw it up here, if I change this 1.8 to 1.91, that gets squared. So that should have a big change on the mass that we were using. That's why the mass was so off. Something less devilish.
Point 739.
So that's non-trivial. So 0.739. So we got to throw on, not quite, an extra 100 grams. We got concurrence on that value somewhere? All right, so we got 0.513. We got 0.613. I got 713. I got 733. I got 0.73. All right, so let's check this out. How close are we? Super close. Super close? Cool. So this thing completes 4 trips in the time that thing completes 2 trips. What's that? Smell me? 1, 2, 3, 4. This thing does. 4 trips, 2 trips. Ish. What might be a problem with the setup here? Here's how I got those values for the spring. So I held the cart in place. I pulled the spring 10 centimeters, about 0.9. Pulled it 20 centimeters, about 1.6. I pulled it 30 centimeters, about 2.3. What does that have? Second spring. Is the second spring going to impact the amount of force felt by the cart? Yeah. So we don't have one spring with the K value big, we have 2 springs with the K value big. So if you look at the equation real quick, we double the value for K, make that 16. What happens to the mass? Doubles. So what does that shake out to?
1.1479.
AKA about 1.5.
Yeah.
Okay. So let's try that. This one is not a hook, so that's just what do you think? Pretty close. Do it all at once. Ish. Okay. So we tie all these together. Hey, something else I need to just show you really quick regarding pendulums, so I don't have to make you do a lab. So we have 2 different types of pendulum bobs, aluminum and steel. So just give those a little shake test. So those are like a factor of 10 different in terms of mass, but you can see here. They're swinging together because I have them the same way. So with regards to pendulums, mass, that's not it. All right. Speed up passes now. So, well, I know that. So let's get it done. All right. Cool. So let's roll back on over this way. Chase you down and catch a It's no fun if you don't run. All right. So trying to tie all those things together. So we got that bright light source on the ceiling, shining down from above. And then you got that pendulum. And below the pendulum, I probably should have set this up so we had the card underneath there. But the pendulum bobs at these different positions are going to cast shadows, right? So here's the cart in the middle. Here's the cart at one end. Here's the cart at the other end. But that shadow from the pendulum would always stay on top of the cart. When is that shadow moving the fastest? When is it moving the slowest? Run that by your neighbor real quick. Speed of the shadow. And so this kind of represents that equilibrium position here right down the center. That's x equals 0. And then here we have x equals a. And here we have x equals negative a. We could tie that into the record player, okay, if I try to carefully draw. I thought you said carefully, Mr. Harden. All right, let's try that again. Yeah, I'll buy that. Okay, if I carefully draw a circle here of radius a, then here's the coin at that position, the far right. Here it is at x equals 0. Here it is at negative a. Here it is at 0 again. Okay, at any other points there, you can imagine as it's going around the circle, it undergoes some angular displacement. For Greek purposes, we're going to call this angle phi. Okay. At that angular displacement, the horizontal projection of the position is just this right here. Okay. This would be x. And the distance from the center to the outside is always a. So my position x is going to be equal to a, the maximum displacement, times the cosine of that angle. I don't like calling it phi. Let's just call it theta. Theta. So when theta equals 0, x equals a. When theta equals pi, what is x going to equal? That would be right here, yeah? So cosine of pi or cosine of 90. Jeepers. Why do I keep doing that? Pi over 2. Thank you. Cover your teammate. So when theta is pi over 2, x is 0. Now I want that. Now when theta is pi, cosine of pi would be -1. So we get x is equal to -a. And when theta is 3 pi over 2, x is again equal to 0. So at those various positions, that's how we calculate the horizontal projection of the shadow or of the circular motion. So recall from earlier in the year that the linear displacement delta x equals v times t if we've got a constant velocity. And the rotational equivalent would be the angular displacement is equal to omega times t. And so I can turn this into a time-dependent expression for position if I sub this in place of omega. So x equals a times cosine omega t. Now, something I'm neglecting up here, things don't always start at a position of 0. So I would have to have the initial position, and here I would need to have the initial angular displacement. So there's the time-dependent expression for the position as a function. Well, that is how that works. Position as a function of time. Where do we need to go with that? Well, we talked about what the x position is at certain angular displacements there. We can take this expression for position as a function of time, and if we take the derivative of that, that's going to give us our velocity. To do that, though, we've got a function within a function there. We've got a constant times the cosine of omega t plus theta naught. So we've got to do the chain rule thing here and take the derivative of the inside and multiply that by the derivative of the outside. So inside I've got omega times t to the first plus a constant. I take the derivative of that with respect to time, I'm going to end up with omega times t to the 0th. And so the derivative of the inside is just, oh, that's a terrible omega. It's just omega, and I want to multiply that by the derivative of the outside. A cosine shmia, the derivative of cosine shmia is going to give us negative sine shmia, and I've got that a there because that's a constant. And then if we kind of think back to yesterday, we were talking about when are these things at a maximum and when are these things at a minimum. As far as velocity is concerned, the horizontal projection of the velocity at A is 0 because all the velocity is directed vertically, right? Similarly, over on the side here at negative A, all the velocity is projected in the Y. So the horizontal projection of velocity would be 0 at those 2 points. It's going to be at a maximum when your x position is 0. Okay, so pi over 2 and at 3 pi over 2. Negative omega a sine pi over 2, that's just going to be negative omega a times 1. Okay, so when it's up here at pi over 2 for an angular displacement, you're going to have the maximum negative velocity. When you're down here at the bottom, you're going to be sine 3 pi over 2. You're going to end up with positive maximum velocity. But that's how we're getting the maximum velocity. And then we've got velocity. So if we take the derivative of that with respect to time, that's going to give us the acceleration. So I do the chain rule again. So the derivative of the inside is again omega. That's going to give me omega squared out front. And the derivative of the negative sine of x is the negative cosine x. So I'm going to get negative omega squared cosine omega t plus what I'm calling theta naught, but that's not how it works with the College Board. So we've got position as a function of time. We've got velocity as a function of time. We've got acceleration as a function of time. But if you look at acceleration as a function of time, this shows up in there, right? Here I have a cosine omega t plus theta naught. So I can just go ahead and do a substitution and get acceleration as a function of position as well. Acceleration as a function of x, negative omega squared x, right? Because this whole thing right here equals x, and it showed up right there again. So your most positive acceleration occurs when you have your most negative x position. Your most negative acceleration occurs when you have your most positive x position. All right. So that's all that jazz. On the equation sheet, that just shows up as this one. Okay. So if we unredact this, if you want to write this in on your redacted version, here's what they're telling you. And we were saying A for amplitude, that's the x max. But otherwise it's the same thing. So calculus kids, you've got that one expression on there. If you can take the first derivative of it, you can get the velocity as a function of time. If you can take the second derivative of it, you can get the acceleration as a function of time. Not in calculus, doesn't mean your boat is sunk. You're just going to need to know these other expressions. There you go. All right. So I think that's it for me talking today. So with the chunk of time you got left, if you want to work on the mastering, that'd be super cool.